Earth Science, Chapter 4, Plate Tectonics. Last week we talked about geologic time, and I moved Chapter 8 ahead of Plate Tectonics just because I think the getting used to thinking about about time is really important, because time deals with physics as well as geology. I wanted to put that in early. And that's a paradigm shift if a person isn't used to thinking about what we might call deep time. And plate tectonics is another paradigm shift. One of the reasons I think taking earth science is important is because having these paradigm shifts in how we may think on an everyday basis is a good way to think bigger. And it certainly has helped me think bigger over the years than just the nature of time that we humans operate under. Plate tectonics is a marvelous concept, and so what we're studying here in Chapter 4 is key to understanding all kinds of systems and interactions between systems here on the Earth. An example of a paradigm shift is Santa Claus. I don't know how you were raised, but I was raised to think in terms of Santa Claus. And when we had kids at home, they're all grown now, we had some fun with Santa Claus because I enjoyed the idea of doing Santa Claus, and my wife had other ideas, and the kids had this. We had this fun game about Santa Claus, and so I'd wrap presents with Santa and play the game, and the kids learned to think it was fun. But it's a paradigm shift if a child really believes in Santa Claus. I remember that I experienced that with the Easter Bunny. When I was in second grade, my dad asked me to come hide Easter eggs for my brothers. Well, before second grade, I thought the Easter Bunny hid Easter eggs. In second grade, I got to go hide them for everyone else. So that paradigm shifted for me. Well, plate tectonics is a big paradigm shift, and it's a paradigm shift that for me has happened over my lifetime. So you may have some examples of a paradigm shift or a cultural paradigm shift. The globalization of labor and interaction globally is a paradigm shift. There's all kinds of paradigm shifts that we're experiencing, and I think as I get older, it's more difficult to deal with these kind of paradigm shifts because you get kind of set in your ways. Well, the Earth's surface is divided into two major elevation zones: land and shallow oceans, and deep ocean water. And one of the reasons I have the Bible verses that go with this earth science class is because I think with the paradigm shift, one can read those Bible verses differently than one would have read without that. And one of those is this idea of God having a line where the oceans will never cross. That line is the difference between these shallow and ocean, these ocean beds, these deep ocean floors, and the land and shallow oceans. There's a line there of specific gravity where the oceans will not cross. I think that's exciting to learn those kind of things about what we observe in God's creation. An early 20th century paradigm is that the Earth was slowly cooling and contracting as heat was lost, and therefore mountains were wrinkles formed by contractions of the surface, and that collapse formed ocean basins, and continents and oceans were effectively fixed in place. Very different than what we learned with plate tectonics. But that was a paradigm shift in the early 20th century, or paradigm of a model of how the Earth trying to explain why we have features on the Earth the way we do. And it was a model that attempted to do that nobody accepts anymore. But it was true back. Alfred Wegener created an alternative paradigm, and that was one called continental drift. And he found, for example, South America looks like it fits into Africa, and so he took that idea and figured out a way to have the continents match up together. And when you look at, and we'll look at the seafloor spreading section in a bit, but he found all kinds of evidence why that could be, and everybody poo-pooed it and thought it was a dumb idea, but it turned out that it's right on. What he did is he matched up things like similar fossils across continents. We talked about index fossils. Well, it's the same kind of idea. So you take a fossil and you find a bed that looks like it's similar between Africa and South America, and it matches up. And here's some examples of fossils that match between South America and Africa, between Antarctica and India, and between Antarctica and Australia. There's a continuous mountain belt that formed when Pangaea is reassembled, and so we can reassemble these continents and find a mountain belt that goes across from one to the other. The field of paleogeography is really interesting. In other words, ancient geography, and that field likes to put these together. Wegener's observations also talked about, noticed that there were geologic formations that matched up together, things like unusual rock sequences that matched up in the same location between South America and Africa, or a shallow continental shelf that matched up between the coast of Brazil and West Africa. And if the continents were together, then they would match. A very different idea than what we talked about at the start of this lecture with the idea of the planet contracting. Paleoclimates matched up. You can see evidence of a thick ice sheet throughout the southern regions, and you can see evidence of glacier deposits in each of these continents, that when the continents were together over the South Pole, they would have glaciers that could not have been there otherwise if the continents were where they are just today. There were rocks that formed in tropical conditions in North America near the equator, and these coal swamps would have moved with the change of continents. You don't get coal swamps on at the poles. So Wegener's continental drift hypothesis was not widely accepted because he could not explain how the continents moved, and supporters of the contracting Earth hypothesis came up with alternative explanations for some of Wegener's observations. For example, land bridges that allowed fossil organisms to move between continents. So he came up with the idea, but because he did not have a mechanism for why it happened, it was not widely accepted. Just shows you just how egg-headed or pig-headed scientists are to me. You get a good idea, and it also shows you just the whole change management principle. I teach change management in a corporate setting, and one of the rules of change management is when you have a new idea, only 7% will jump on that idea quickly. You have to prove prototype the idea to get another let's say, I'm just picking a number, like 20-25%. but you have to take all the risk out of the change in order to get a majority of people to accept the change. Well, scientists aren't any different. Scientists don't like changes either. And so for somebody to come up with a new idea, they have to take the risk out of it. And in this case, the risk is a risk of ideas. The risk is one where, hey, if you can't tell me how it's going to happen, then it's too risky to believe it. So here's an example of his idea. You have different plates, and the plates fit together and form a, it's obvious to us that they fit together, where they should fit together. But it's certainly not, we don't know how the plate broke, but it broke. Well, if we were scientists, then we'd say, well, we don't believe the plate goes back together and broke because we don't know how the plate broke. Right. So which lines of evidence were not used to support Wegener's continental drift hypothesis? Well, earthquake locations were not one of them. He did use distribution of fault, and the rest of those. Okay, so science follows some basic rules. It's tentative, it's based on observations or experiments, it's predictable, it offers a natural cause for natural phenomena, and so a question there to think about. Was the development of Wegener's continental drift hypothesis consistent with the characteristics of good science? Yeah, it was. A good scientist won't accept something as science unless there's evidence of it, unless you can understand how something happens. And so having his hypothesis accepted went through the scientific method, and that's okay. I'm ragging on scientists a bit when I talk about being pig-headed in change management, but that's just the nature of science, that things change, and it's hard to you're not going to accept those changes without strong evidence and a lot of arguing to get it done. And that was certainly true with Wegener's continental drift hypothesis, which now is I suppose it's a theory, but it's pretty factual. Earth science, plate tectonics, evidence from the seafloor. In the decades after Wegener's research, there were a number of observations that helped with the new understanding of Earth processes, and those helped give us a mechanism of why the continents might have spread, which led to acceptance of Wegener's continental drift idea, but broadened it into a whole field of plate tectonics. And those included seafloor topography, age of the seafloor, heat flow, volcanoes, and earthquakes. And the processes around those and where they're located and what's going on at different parts of the world with all 5 of these all supported plate tectonics. Some key features of the seafloor topography include a continental shelf, and we see one there on the east coast of North America and the west coast of Africa. It's a narrow, shallow ocean surrounding continents. Also an abysmal plain. We see one east of Bermuda. It's a relatively level seafloor, and in between the active oceanic ridges and where the seafloor rises up into the continent. Also oceanic ridges. You see it marked there in the middle of the picture. This is a really long submarine mountain chain that's full of volcanic activity, and it even reaches the surface in places like Iceland. And then also oceanic trenches, for example the Puerto Rico Trench, where the deepest part of the ocean is where one part of the seafloor dives under another part. Oceanic ridge system, you see a light purple mark there. Zippers all over the world. It's like a big zipper that pushes, that opens up. It's often found toward the center of the oceans because over time that ocean has pushed apart the continents in between them. Oceanic trenches are found adjacent to some continents or island chains or along the margins of oceans. Just depends on where the plates match up and whether they're going to dive down. One plate's going to dive down under another. For example, the Peru-Chile trench, just to the west side of South America, is where the one plate dives under another plate, and as that plate melts, it creates the Andes Mountains. This should be a fairly straightforward question because the oceanic ridges, mid-ocean ridges, are mountain chains. So which one of these is a mountain chain in the mid of the ocean? Well, C is a mountain chain, as you can tell. The age of the ocean floor is also evidence of seafloor spreading. If you look at the colors, the similar colors are similar ages, and these ages are all measured using radiometric dating. And we talked about radiometric dating earlier when we talked about geologic time, which is one reason I wanted to talk about that section before now. So you can take rocks that are gathered from coring under the seafloor and date those rocks using multiple types of radiometric dating, and they match up, which means that the red, younger than the yellow, younger than the green, younger than the blue, the ocean has spread, say between North America and Africa, or between the western side of the Pacific, or the Pacific and the eastern side of the Pacific. Here's a little closer picture of the same kind of thing. You have youngest rocks located in the center of the ocean basins, the oldest rocks along the margins of the ocean basins, and the age of the seafloor rocks increases symmetrically from near the center of the oceans. Really, really strong evidence of seafloor spreading. So here's a question: which statement is true about the relationship between age and topography of the ocean floor? Well, D is true. Youngest seafloor rocks occur along ocean ridges. Yeah, let's talk about heat flow, volcanoes, and earthquakes. Heat flow varies systematically around the world. So if we look at our colors, red is hotter, purple is cooler. Notice where the hotter parts of the ocean, notice where the hotter parts of the earth are. Well, along the ocean ridges. And so that supports the idea that you've got hot lava coming out of those ridges, pushing apart and creating lots of heat flow. Where are the volcanoes in the world? Where are the active volcanoes? Well, they're found right along ocean trenches, because you have one plate subducting or going down under another plate. It melts, and that melted rock differentiates or separates, and the lighter minerals of the rock separate and float and come up and create volcanoes. And so you have what's called a ring of fire around the Pacific Ocean, where these volcanoes, because the whole side of the Pacific Ocean is where oceanic plates are diving down underneath continental plates mostly. So most active volcanoes are found near oceanic trenches. There's an exercise I have you look at when we get to volcanics, where you look at where active volcanoes are around the world, as well as active earthquakes. So keep this in mind when you get to that exercise. Okay, here's where earthquakes are located. The shallower earthquakes in yellow, the deeper earthquakes in purple and red, and or the colors other than yellow, maybe we'll just say that. And notice that there's lots of shallow earthquakes along the ridges. it almost exactly matches. It really does exactly match. Whereas the deeper earthquakes are along the trenches. And you can even look at these earthquakes and measure earthquakes along what's called a Wadati-Benioff zone, where one plate is subducted under another plate. In this case, oceanic lithosphere is being subducted under continental lithosphere. And you can follow those earthquakes right along where that plate is being pushed up under another plate. Well, here's some observations that support seafloor spreading. On older seafloor, there's no volcanoes and earthquakes. And on oceanic ridges, you have high heat flow, younger rocks, and an elevated seafloor. See where the magma is coming up on that ridge in the middle of this ocean floor. And ocean margins of the trenches are older seafloor and volcanism and earthquakes. You can see a passive margin is a margin where it does not have an active trench. On the left side of your picture, the passive margin is just moving away, but there's no trench going under it or anything. One thing that happens with the ridges, the oceanic ridges, is magma rises from the mantle, and that magma differentiates, and we'll get into that differentiation when we look at rocks, because that's how different types of rocks form. But it rises from the mantle, and then it cools, and so you have this constant changing of the surface of the earth with the rising magma, the pushing apart of the ocean floor, and then the melting of those rocks and the separation of the heavier material from the lighter material when the oceanic material melts. And that lighter material forms the continents, and thus, as it says in Psalm 104, God has created a boundary that the oceans will not cross, because the lighter material is floating on the heavier material. The continental crust is lighter or less dense, and the oceanic material is more dense. Let's think about some interpretations from seafloor spreading. The older seafloor descends into a mantle at an active margin on the right side of the picture. Those melting rocks form volcanism. Earthquakes are where an old seafloor or seabed is consumed, so you get earthquakes at the little yellow sparkle, little yellow explosion kind of pictures. Okay, some questions. Additional observations about the magnetic properties of seafloor rocks support the seafloor spreading hypothesis. Okay, why does the Earth have a magnetic field? Well, it has a magnetic field because there is molten rock or semi-molten rock in the outer core, and heat is generated from currents in that outer core, and the Earth's rotation mixes those currents. So the Earth becomes dynamic because of that, and that dynamic Earth allows life to exist on the Earth. Here's a picture of the Earth with the core and magnetic flux coming from that core. Notice that there's a geographic North Pole as well as a magnetic North Pole, and they're not quite the same. They're about 11 degrees different. And notice that magnetic north is toward the geographic North Pole today. It hasn't always been that way, and we'll talk about that in a bit. But today, that's the case. So the Earth's magnetic field can be defined by direction, i.e. the field points toward the magnetic poles, as well as inclination. The field points down in the northern hemisphere and up in the southern hemisphere. Notice what we're talking about is the direction of the arrows. Notice the direction of the arrows in looking at the lines of magnetic flux. So the inclination is greatest at the magnetic poles, and the field is more horizontal at the equator. And you can see the magnetic lines of magnetic flux show that. When you have magnetism, some minerals align themselves in parallel with a magnetic field. Iron is one of those minerals. So when magma cools that has those minerals in it, then they line up. And so you can take a melted magma, and then just like water, and then cool it. And water makes ice and it cools. Well, rock does the same thing. Magma cools and it makes rock. And when it cools, the minerals that are magnetic will line up and point toward magnetic north. Well, those are preserved, and the field that describes that preserved magnetism is called paleomagnetism, or ancient magnetism. So here's a question: which United States location has the greatest magnetic inclination field that is closest to vertical? Well, remember, it's horizontal toward the equator, vertical toward the north. So surprise, surprise, the furthest north is the highest magnetic inclination. Another question: the magnetic North Pole has migrated northward over the last century, so how did magnetic inclinations readings at Chicago change between 1900 and 2000? Well, the inclination decreased because the magnetic North Pole has migrated northward. And remember, inclination is flatter toward the equator and more vertical toward the North Pole. Now, over time, the magnetism has reversed. North Pole hasn't always been North Pole. So the paleomagnetic records indicate that magnetic poles have switched positions many times over Earth history. Normal polarity is when a negative magnetic pole is toward the geographic North Pole. And that's what we have today. So the lines of magnetic flux are inclined downward in the northern hemisphere and upward in the southern hemisphere. And so here you see the red lines of magnetic flux doing that. But you get a magnetic reversal, and that's a reverse polarity when the positive magnetic north is near the geographic North Pole. And that's where the lines of magnetic flux are inclined upward in the northern hemisphere and downward in the southern hemisphere. So when you do that, your magnet's going to point south. I mean, your compass is going to point south instead of north. The same with the rocks. When that magma cools and the rocks have magnetic minerals in them, they'll point the other direction. So we have a normal polarity and a reverse polarity. In each period of normal reverse polarity averages, and remember, that's just an average, about 250,000 years. The longest one of where the polarity has not changed has been tens of millions of years, and the shortest has been tens of thousands of years. It's been a long time since the polarity changed, so maybe it'll happen. So what happens is, with this paleomagnetism and seafloor spreading, here we have a little compass, and we're pretending that compass is a rock mineral that is magnetic, and it comes, the material that makes up that mineral is in the magma, and it cools, and when it cools, it's a high iron content rock, for example, and then it will line up north-south and point to magnetic north. So when you do marine surveys, you can measure the strength of the Earth's magnetic field from these rocks. And there's a strength higher in regions of normal polarity and lower where there is reverse polarity. Here's a cartoon. So over time, you get magnetic polarity changes. Notice that we get flips between north and south, normal and reversed, over time. So we can look at the okay, we're going to play it again here, I think. And we're going to play it again here. Flip, 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 flip. So the colors there are one polarity and the gray is another polarity. Okay. Okay, so with paleo-magnetism and seafloor spreading, we can look at these bands and tell, and they match right up in a symmetrical pattern on either side of the ridge with normal or reverse polarities. And here's an example of what one of those surveys would look like. You have positive, negative on both sides, and they match in similar distances from the middle, from the middle of the ridge. Okay, so here you see a cartoon on the left with the compass going back and forth, back and forth. The blue is a similar age on both sides of the ridge. The green is similar age, and the gray in between the blue and the green is a reverse polarity. Another example from the Juan de Fuca plate. You'd see a time scale with magnetic patterns in the ocean floor. And if you look at the basalts that come on both sides of that, you can see the polarity changes in those basalts. And basalt's a rock that has lots of iron in it, and so that's one reason that basalt is a heavy rock that gets made on the ocean floor out of that type of volcanism. So that magma that turns into basalt has lots of iron in it, so you get lots of compasses to check. And there's basalt on land too, and you can do the same thing on land and measure the polarity of the rocks on land. Okay, I'll finish up with another cartoon here. Get upwelling of magma, and then you get a ship going over that, and it's measuring that with a magnetometer what you're getting on either side of the ridge. You just take a ship over there, do a magnetometer, and you can measure what's at the bottom of the ocean floor. Earth science, plate tectonics. The Earth has three compositional layers: the crust, the mantle, and the core. And you can see a diagram of the Earth there that shows those different layers, and you can see a more detailed square of the very top of the part of those layers with the crust, and underneath that is the mantle. In the crust and mantle area, the very top parts of the Earth, we have a lithosphere, which is a rigid layer composed of crust and uppermost mantle, and it's divided into these mobile tectonic plates that are the basis of plate tectonics and how they affect us. Underneath that is a weaker layer in the upper mantle we call the asthenosphere, and it's more of a kind of you can think of it as kind of a plastic. Plates around the world, it's worth knowing that a lot of these plates are named after the continents, but some of them aren't. So, for example, we have the African plate, the South American plate, North American plate, Eurasian plate, but then to the west of South America is the Nazca plate, and then you have the Pacific plate, and then the plate just north of California, west of Washington, is the Juan de Fuca plate. So there's 8 major plates, and the Juan de Fuca plate so small it'd be a minor plate. Major plates are the African, Antarctic, Eurasian, the Indian Australian plate, the Nazca plate, North American plate, the Pacific, and the South American plate. And you need to know what those names of those plates are. That's important. Most plates are composed both of continental and oceanic lithosphere. Some are pretty much just ocean ridges and trenches and oceanic kind of material. The plates interact along their boundaries, and we've talked a little bit about that when we were in the lecture on seafloor spreading. And but these interactions between the plates create volcanoes, earthquakes, new rocks, build material for continents, pull the continents apart. All these interactions are things that have big impacts on humans. Let's talk about how the melting of rocks produces magma. At the formation of lithosphere at oceanic ridges and the generation of volcanoes near the oceanic trenches. There's 3 changes that lead to partial melting. So when we talk about partial melting, we're talking about taking rocks that are like ice cubes, they're hard, they're rocks, and then melting them, partially melting them. Well, it's increasing temperature, decreasing pressure, and the addition of water all lead to partial melting. So, increasing pressure to start with. Well, as temperature increases with depth, the increase of pressure impedes melting. But when you're close to magma, it gets hotter. So you have solid rock, and when that moves closer to a magma, it partially melts. Well, if you take that rock and it rises toward the surface, it decreases in pressure, and it will also melt. So the way to think about this is to start with the X, and if you move to the right, you're increasing in temperature, and it's going to melt. But if you start with the X at exactly the same spot and move up and decrease pressure, it's going to melt. So you have a pressure temperature diagram, and you can move vertically or horizontally along that pressure temperature diagram, and it will melt either way. Okay, you can also add water, so we're going to take that same X and just leave that X in the same spot. But if you add water to the environment, what happens is that it changes the curve of where you get partial melting from where you see it in the upper diagram to the lower one. And so you add water and you get partial melting just by not moving. The rock stays where it is, you add water, and it starts to partially melt just right where it is. It's simply because of the nature of adding water to the mix. New lithosphere forms at oceanic ridges. There, we've said it a couple times, but we see the magma coming up, and that's where you get new lithosphere, new crust, and you get a generation of earthquakes and volcanoes, where older oceanic lithosphere is destroyed at a subduction zone. Subduction zone is where that oceanic crust is diving down underneath continental crust or other oceanic crust. And the earthquakes are marked there, and you can see where the earthquakes are on a graph, and actually tell the depth, and from the earthquakes know where the subduction zone is. Continental lithosphere is not consumed at a subduction zone. Continents can break up, but the total volume stays the same. Back to that Bible verse I was mentioning in Psalm 104, God has created a boundary where the waves cannot cross. Continents, you put continent under the ocean and it's going to bob back up again just like a cork because it's lower density. And we're always going to have land on the earth because of that. So God's created a mechanism to keep us not having to learn how to swim. Older oceanic lithosphere is destroyed at a subduction zone, and we talked about partial melting, but there's a lot of water that comes down in with that subduction zone, and that helps create partial melting in that overlying plate. And then the magma goes ahead and rises, and you can see volcanoes coming from that rising magma. Now, most continental margins are not plate boundaries, and we call those passive margins. And so it's a margin where you don't have a lot of activity, so it's called passive. Okay, here's a question. How many plates are in this image? Well, we have 5 plates. So we have a oceanic trench, oceanic ridge. So we have a plate down there at Z, and we have a plate there at Y. We have a plate at X. We have another plate up where C is, and another plate that's not marked in between the blue and the red lines under C. So the blue and the red lines are what's actually separating the plates. I'm just using the letter for convenience. Okay, let's talk about the rate of plate movements. And if we take Hawaii, Hawaii is formed over a hot spot underneath the Pacific plate, in the middle of the Pacific Ocean. And as that plate moves, the hot spot pokes lava up through the plate and creates volcanic islands. So the island of, I'm going to crucify the names here. Kauai is 5 million years old, and it's moved 600 kilometers since its formation. About 12 centimeters a year. This present hot spot is at the star, just southeast of the island of Hawaii. So won't happen in our lifetime, but at some point there'll be a new island that's formed, and the island of Hawaii that actually actively has volcanics on it now will move on to the northwest. In 2012, I was at giving a talk at the Evangelical Theological Seminary Society conference, and my friend Greg Davison out of the University of Mississippi gave a talk also, and he's with our Solid Rock Lectures group, where we help train pastors and theologians about geology. But he used the Hawaiian Islands as a really good example of why it just does not work to hold a young Earth position from looking at science, because the Hawaiian Islands are a good example where you can't have Hawaiian Islands like we have them with young Earth mechanisms. Okay, the rate of plate movements are shown here. The purple line is 5 centimeters a year, and so you see plates that are moving very quickly and plates that are moving slowly. So for example, the Pacific plate is moving very quickly to the west or the northwest, and the Indian Australian plate is moving very quickly to the northeast. which is one reason you have so much earthquake and volcanic activity in between the two, because they're both very busy right there at the deepest trench in the world. Marianas Trench is right there off the Philippines. Okay, so the directions of plate movements. Can you predict which plates will get larger and which will get smaller over the next million years? Well, what we'd have to do to answer that question is look at the different rates of motion and see what's happening with those different rates. The fact that let's take African plate. I think that's a pretty interesting example. It's moving in the same direction as the Indian Australian plate, so it's probably going to keep getting bigger because there's nothing on the east side of it that's pushing it and making it smaller. Same with the Nazca plate, it's just going to get bigger. Okay, how many plates are there in this image? Well, there's 3. So we have the one to the left of the ridge, to the right of the ridge, and then to the right of the subduction zone. Now, where do we get the energy for plate movements? Well, the mantle has convection cells that carry hot material from the Earth's interior toward the surface and then transport cold material to depth. There's 2 potential hypotheses which interpret plate tectonics to be driven by upper mantle or the whole mantle convection. One is an upper mantle convection model. Another one is a whole mantle convection model. And so we see both there. One basically you have convection currents just like you would in a boiling pot on the stove, and the upper mantle is a smaller convection current driven by a lower convection current below, and the one on the right is the whole thing is one big convection current. And I'm betting on it's going to be more complicated than either one of those. There's probably multiple convection cells, but that's just what I think. Okay, question: the continental crust at Y is moving toward which direction is Y moving? Well, think about an oceanic trench, an oceanic ridge. Trench is forming crust, ridge is, a ridge is forming crust, so the red is where crust is forming, the blue is where crust is being destroyed or melting, and so along the red to the northwest of Y, crust will be forming, pushing Y toward the southeast. The question: the island of Bermuda, and it's circled in yellow there, is a former volcano on the floor of the western Atlantic Ocean. Approximately how far and in what direction would this island travel in 100 years? Well, the question is, how fast is the Atlantic spreading apart? And we can measure it with satellites as about 2 centimeters a year. You can actually measure Bermuda moving at 2 centimeters in a year with a satellite. Okay, another question here. Review the map below and identify which pair of locations is moving closer together as a result of plate tectonics. So which locations are moving closer together? Bombay compared to Sydney. So Sydney and Bombay are on the same plate. So you wouldn't think they're moving closer together because they're on the same plate. So B, Hawaii and Tokyo. Now they're on different plates. And there's a subduction zone to the east of Tokyo. So Hawaii is moving toward the northwest, Tokyo toward the southeast. So they might be moving closer together. New York and London. Okay, well there's a ridge between them, so they're moving further apart. Cape Town and Sydney. Cape Town and Sydney are on a ridge, so they're both kind of moving different directions. So here we are, Hawaii and Tokyo, like we thought. These are the kind of questions it's important for you to think about, just because a lot of this is not memorizing information. It's taking information and looking at the system and then using that information to then answer a question. Because the whole goal here is to help you think systematically. Okay, so think about the phrases that are most appropriate on the location of the Venn diagram. So you have divergent boundaries versus convergent boundaries. Well, divergent are spreading apart, convergent are pushing together. Divergent are ridges, convergent are trenches. So rocks on either side of the boundary are typically of different ages. They're different ages, so that would be convergent. Whereas rocks on either side of a ridge would be the same age. Okay, the Nazca and South American plate boundary are convergent boundaries. Convergent boundaries are trench kind of boundaries because they're pushing together. Oceanic lithosphere may be present on both sides of a plate boundary on either one. And only young ocean lithosphere is present in divergent boundaries. And plates move away from each other are divergent. Plates moving toward each other are convergent. Convergent plate boundaries are associated often with volcanoes. Magma rises to the surface at or near the boundary on both of them. Totally different mechanism on the boundaries, but magma is coming to the surface on both. Remember, it's coming to the surface from the mantle on divergent and from partial melting in convergent or trenches. Okay, number 10. Continents get pulled apart in divergent boundaries. That's why we have the Great African Rift Valley that goes right up through the Red Sea up into Israel. That's a divergent boundary. And then continents combine, like at the Himalayas, in convergent boundaries, where the Himalayas are formed from the Indian plate crashing into the Eurasian plate. Mountains are present where continental lithosphere is involved. Yep. And number 13, chains of volcanic islands form in convergent boundaries, where you have a plate that's one oceanic plate diving down underneath an oceanic plate. The magma comes up, and that magma eventually will form islands that rise above the surface of the ocean. By the way, the tallest mountains in the world start out from under the ocean and come on up from that. They aren't like Mount Everest, but if you start out under the ocean and come up, they're much taller than Mount Everest. Number 14, continental lithosphere on one side of the plate boundary, oceanic lithosphere on the other would be convergent. And divergent boundaries are oceanic ridges. Divergent would be, an example would be the boundary between the Nazca and Pacific plates. And deep earthquakes occur in convergent boundaries because you have subduction of the oceanic plate underneath the continental plate, and it dives down really deep, so you get deep earthquakes. So we've talked about divergent and convergent plate boundaries, but there's another type of plate boundaries too, and that's a transform boundary. That's where the plates are slipping across from each other. A good example of that is the San Andreas Fault in California. So here's examples of the three types of plates. You have a transform, convergent, and a divergent boundary. A divergent we've talked a lot about. Convergent we talked a lot about, but a transform boundary we might find where the North American plate is slipping by the South American plate. They're just edging on, and one's going one way, not going, the other one's going the other way, but they're not diving across each other. They do form earthquakes though. Okay, 3 stages in the evolution of a divergent boundary. And here we have talked about the Red Sea and the East African Rift. And a lot of these times they form in triangles. And you notice there's a breakup where you have the Red Sea, the Gulf of Aden, and the East African Rift are the three legs of this triangle. These divergent boundaries try and break apart at that spot. So then after they start to break up, eventually you get a narrow sea in between them. And so you could think of the East African Rift as the beginning of the breakup, and the lakes you find around the rift, like Lake Tanganyika and Lake Nyasa and Lake Turkana, Lake Albert. And by the way, as a kid, I used to live in Uganda and Kenya, and had a lot of fun going and look at those lakes and volcanoes around the Rift Valley. So if you get a chance to go look at the geology there, it's worth a trip. Not just the animals, but to look at the geology there, because that's where you have an early place where the plates is starting to pull apart. Then after they pull apart some, then they start to get flooded, and you get things like the Red Sea and the Gulf of Aden and a narrow sea there. Then eventually they keep on pulling apart, and then you get an ocean. So it could be that there'll be an ocean formed where the Red Sea is now, unless something forces them to go back together again. But if you think of what you see there in the Rift Valley and the Red Sea at the Gulf of Aden, that may have what it would have looked like when the plates between Africa and South America started to pull apart, very early part. And now, why is that important? Well, if you're looking for oil, that's a great place to look for oil on either side of those plates. And so we find a lot of oil, say, in Angola. And so you need to understand, if you're looking for oil and you're a geologist, you need to understand about what happened during the formation of the early pulling apart of those plate boundaries, so you can predict where to go drill for oil. Okay, so here's a question. Which of the four diagrams best represent a divergent plate boundary configuration? Divergent means pulling apart, so that would be B, because the arrows are going away from each other. Pretty easy question. Which of the locations of the map represent examples of divergent plate boundaries? Remember, divergent, pulling apart. That's important to know this. Think about pulling apart, pushing together, or slipping across each other. So divergent, well, we just talked about the Red Sea. That's one. There's an oceanic ridge between the Antarctic and the Pacific plates. And there's a mid-Atlantic ridge. So those are three divergent ones. So it's a C, 2, 7, and 9. Okay, three types of plate boundaries. We've been talking about that. Now, magma generation at the convergent boundary, we talked some about that. But here's an example we haven't really looked at, and that's where one oceanic plate dives down and subducts under another oceanic plate. And where you get that, rising magma will form a chain of volcanoes along that ridge, along that plate boundary. A convergent boundary, another example here. Older lithosphere is consumed in the subduction zone. So we call those island arcs. Okay, and this is just backwards of what we were looking at, but here you have a subduction zone where you have oceanic crust diving down under continental crust and forming a volcanic arc, only it's a continental one. And here you have continent converging with another continent notice you aren't getting volcanism, but you're getting a steep mountain range here. Example, this is the Himalaya Mountains, where you have one continent crashing into another continent, and the land has to go somewhere, and it goes up. Okay, looking at the crustal thickness map, look where the thickest crust is. Well, over the Himalayas it's thick, and over the continents it's thick. So convergent boundaries. It's really thick over the Sierra Nevadas in California, and then also in the Andes Mountains. These are where you have convergent crust, and it gets to be real thick because you have crust pushing down under other crust. So here's a question: which of the locations of the map represent convergent plate boundaries? Well, here's a converging boundary here, 3. Here's one here because the Pacific plate is subducting under the Eurasian plate. And here's one here where the Pacific plate is subducting under the Indian Australian plate and creating an island arc there. So 3, 4, and 5. Which of the numbered locations best represents a plate boundary configuration similar to C? Well, C is the convergent boundary, and so where do you have a western and eastward moving? I kind of want to say a Zax from Dr. Seuss, east and a west moving Zax. Eastern moving plate and a western moving plate, with the western moving plate diving down underneath, or eastern plate diving down underneath. Well, like we said a minute ago, it's at 4, where the Pacific plate dives down underneath the Eurasian plate, and that's why you get volcanoes around Japan and tidal waves. They just had a tsunami in Japan a few years ago, because of that type of plate activity. Well, and also there at number 5. So the answer is C. Okay, 3 types of plate boundaries. Talk about transform boundaries, or where you get the transform plates slipping by each other. You see a lot of these in mid-ocean ridge systems, where you have the ridge, but then with the Rift Valley, but then they get pulled apart or transformed back and forth. And so you don't have the ridge all in one nice neat zipper line, but it gets pulled back and forth, and so you don't have any lithosphere destroyed or created, but it's so you can see the picture shows you blue and pink at one time was one nice long line with the mid-ocean ridge in the middle, but then the transform boundaries that pulled them apart. And a good example of that is the San Andreas Fault in California, whereas Los Angeles is moving north, San Francisco is moving south. So a question about transform plate boundaries. Where's an example? Well, 6 is a good example. we just looked at it. Okay, and here's a reconstruction of the Earth, and notice what India is doing. It's crashing up in the Himalayas. Notice how active the Earth is over time. So MY is millions of years. So we're starting with our little cartoon about 140 million years ago, coming up to present. And as you look at it, you can see, just like Scripture says, the Earth is like a piece of cloth that God is shaking. And it just looks like a piece of cloth moving around to me. Okay, the interior of the Earth, let's talk a little bit about that. The lithosphere is divided into large slabs known as tectonic plates. We talked about that. We talked about this, that there's crust, mantle, and core. We talked about the interior of the Earth has an asthenosphere, lithosphere, and oceanic as well as continental crust, that we haven't talked about what they're made of, and so let's talk a little bit about that. The upper crust is mostly silicon and oxygen. The rocks there are silicates. The mantle are composed of silicon, oxygen, and magnesium, and magnesium is a lot heavier. It's a metal, much heavier than silicon and oxygen. And the core is composed mostly of iron and nickel, and the inner core is solid, and the outer core in orange there is partially melted. And the reason it's because it's not solid, it gives us the magnetic field that we have that protects us from the harm that the sun would do on Earth. There's lithosphere and asthenosphere as two layers in the crust in the upper mantle. The lithosphere is a rigid layer composed of crust and upper mantle, and that's where the plates are. So the plates are in the lithosphere. Underneath that is the asthenosphere, which is more like a plastic or a weaker, we say a weaker layer, but think of when I say plastic, think of like Play-Doh or clay. And here's a cartoon showing us kind of what happens. So you have the hot mantle rock coming up in the ridges, and the convection currents in the mantle bring that magma up to the surface, and as the oceanic floor spreads, it runs into either another oceanic plate on the left or a continental plate on the right. And when the oceanic crust, it has to go somewhere, and so some goes up, some goes down, and when it goes down, it melts. And remember, it partially melts, and the things that affect that partially melting are increased temperature, decreased pressure, or decrease of pressure, and the addition of water. Decrease of pressure happens when you take rock and move it up, and increased temperature happens when you're in proximity of magma or moving down into the earth. And the presence of water happens because it's under the ocean, and water gets combined with the crust when it subducts.